I'm going to be talking about today. So thank you very much, Ingo, for the very nice introduction. I'm very happy to be here, because I'm always happy to come to the University of Stuttgart. It's very nice to come to our close colleagues from down the Neckar, I guess. And also, of course, because Stuttgart is one of the world centers for simulation research. So I'm actually a little bit apprehensive to tell you about our work, and we'll see how controversial I can make it. So the title of this talk is Probabilistic Simulation Methods for Scientific Machine Learning, because my group is called Methods of Machine Learning. And it's also has this title because there's a really strong emerging trend within the machine learning community to apply machine learning technology to the scientific process, or maybe the other way around, to include the ideas of the scientific process in machine learning pipelines. And I think there's a lot to do in that direction. So let me tell you why I think that. So here's a cartoon picture of how the scientific process works, as you might find like in a textbook, right? So someone goes out into the field, scientist, domain scientist, they collect some data. That's something they write in a notebook with their hand, right? And then they go back with the notebook to the lab, and then some humans get involved, some scientists who stare at the data, and then they reduce this data, this like lines plotted on some plotting paper, into laws of nature, into equations, typically partial differential equations, maybe like as a sort of a placeholder. And then that stuff, these laws of nature, these mechanisms, that you can feed into a big computer, and that computer can then simulate a natural or technological system. So this is, of course, not actually what happens anymore in science. This is maybe a cartoon from 1905, but that's actually still how the algorithms work that we use to produce this process, because they were founded in 1905. So to give you an example of this, I'm going to use a totally prototypical simulation method that actually is from 1905, and I have the code here. So in other places, I usually have to explain what this is, but maybe in Stuttgart I don't have to. I'm not sure. So this is, first of all, can someone guess what the language is? What kind of programming language is this? This is Fortran and 77. What? No? Yes. So actually, you don't see that much code yet, right? But you can already. Okay. So this is a solver for an ordinary differential equation. It's as you can see. So I mean, I can show you a lot about this code. We don't have to go through the whole thing. What I want to point out is maybe 3 points. The first thing is these algorithms are old. They were written in Fortran. You can see that they were written, in 1993, last version 1996, by a bunch of Swiss guys. They are actually an implementation of an algorithm that was published in, I always get the number wrong, I think it's the 80s, the Dominant-Prince pair. But actually, they are an instance of a class of simulation methods which were invented literally in 1905. So these methods are primordial in a way. They've been around for a long time. And the two other things I want to point out is that they have, of course, because they're good mathematical methods, a very rigorous and precise interface. You have to give to this simulation method initial values and an integration range and a handle to the function. But what you don't find in this list up here is a way to plug in the data, right? There is just a mechanism, but no data. And the other thing about this piece of code is that it's a very typical numerical algorithm, which means that it contains these magical numbers. It's a very rigid structure. It's very precisely derived. If you go to a numerical analysis class, then you'll learn about these Butcher tableaus, and you'll find out that they have a very precise structure, and you're not allowed to change anything. So if you go in and like replace this 35 by a 42, the whole algorithm is not going to work anymore, at least not on paper. So this is, of course, I mean, maybe fine, but it also means that if you have an application in mind that doesn't perfectly fit the mathematical description or task of this algorithm, you're kind of out of luck. It's difficult to think about what you would change in this code to make it do what you want it to do. So I'll go back to my slide, because I think this describes the situation we're in computer science in 2022 quite well. So machine learning is a much, much younger field. It was invented way after this piece of code was actually written. Maybe it's like the first machine learning conference, international conference on machine learning was in the late 80s, early 90s. And as a field, it maybe came of age in like, this millennium. And that means that whenever people working on inference, on learning algorithms, on AI, encountered some numerical problems in their computation, in the computational task that they were trying to solve, and they did indeed encounter a lot of these problems, not just simulation problems, but also optimization problems, integration problems, linear algebra problems, they invariably discovered that there was already code for it. There was already another community like engineering, physics, economics, mathematics, who had solved these problems ostensibly for them. So there were nice Fortran or MATLAB or these days Python libraries that you can use to solve your problem. And that's nice because it saves time, designer time, but it's also a bit dangerous because it means you are stuck with these algorithms. And if you at some point discover that these are maybe not ideal for what you're trying to do, then things get more complicated. And it did indeed get more complicated because contemporary machine learning, poses a few challenges that are not well addressed by these algorithms. In particular, it poses this kind of data-centric view. So simulation methods, with some apologies to all the experts in the room, are essentially algorithms that take a mechanism and then simulate the real world, while a cartoon picture of machine learning is pieces of algorithm that take data from the real world and somehow extract some structure from them, right? Some patterns. So they are sort of opposing directions of problems that they're trying to solve. But of course, in reality, everything is always a mixture of both. So in particular scientific applications of machine learning, we have different sources of knowledge we would like to combine. We have mechanistic knowledge, laws of nature. We have empirical knowledge, numbers that have been collected outside, but they're not coming in on a piece of paper. They're stored on some hard disk in the computer. And maybe also additional like Wager knowledge, like I know that the solution has to look something like a bowl, but it's a bit difficult to write down what exactly I mean. Now, these first pieces of information, this mechanistic knowledge, laws of nature, they don't actually, of course, like in the simulation, we don't actually just write down a law of nature and then we know the solution. Instead, we do something afterwards, which is called computation. So we use the laws of nature to translate them into some computational steps, to collect information from a computer by computing some numbers. So what I'm going to show you in the next few minutes is my personal view on how to best combine these three pieces of information, these three sources of information in a joint inference loop. And it's based on this insight that we actually don't directly use PDEs in simulation. We actually use computers as sources of information by expending energy on a computer to collect numbers that we can then use to estimate what the solution of a simulation problem is. And this is founded or kind of connected to this idea that Ingo already pointed out, which is my personal shtick, which is that you can think about computation in the language of learning. This may seem backward to someone who comes from the other field, but that's my personal view. So numerical algorithms, whether for simulation or for integration, for optimization, for linear algebra, what have you, are algorithms that estimate some unknown quantity, like the solution of some boundary value problem, given results of computations on a computer chip, on a GPU or a CPU or some other piece of hardware. So they estimate a latent quantity given an observable quantity. And that's exactly what machine learning algorithms do as well. They do inference. They infer a latent quantity from data. It's just that normally in machine learning, we think of data as something that's on the disk, and you call for the disk to tell you about those numbers that it has stored. But you can also collect those numbers from a chip. They're still floating point numbers. It doesn't matter whether the bus got it from this side of the computer or from the other side of the motherboard. They're both sets of information that we can use to inform our inference process. And when we think about computation this way, it becomes natural to think about it in the language of machine learning, in particular in the language of probabilistic machine learning, Bayesian inference, if you like, and to think of numerical algorithms that are phrased as active Bayesian learning agents, algorithms that take in a probability measure that describes their task, a prior, and then they perform computations to collect information about the quantity they care about. That's computing a likelihood. and they multiply the prior with the likelihood, and they return a posterior over this problem that they're trying to solve. So that's the hand-wavy view. I'm going to give you concrete examples to try to explain to you what I mean by these kind of algorithms. And I'll use one particular example to make it concrete. And I should also say that all of what I'm going to tell you in the following is the work of my research group. So it's largely work by PhD students and postdocs, many of these people here. In particular, I'm going to be talking about simulation methods. So the simulation part of my group is particularly important. That's Marvin Pförtner and Emilia Magnani and Jonathan Schmidt and Nathanael Bosch, Philipp Tonarp, and Nico Kramer, whose code I might show you every now and then. The other people work on other problems. So let's pick a scientific inference problem, if you like. But of course, I'll have to boil it down to a very simple example so that we can talk about what exactly we mean. So I'll pick a one-dimensional simulation problem that everyone is familiar with. So here is data that this is the kind of curve that everyone in the room knows. If you're older than, I don't know, 10 years. These are infection counts from the COVID-19 pandemic in Germany from the first 1.5 years of the pandemic. So here is where it started. And well, we're somewhere over here now. This is a time series, right? It's a data set that contains numbers. And you remember that depending on where you are in time, so maybe if you're sort of here in November 2020, then we all remember that the natural question on everyone's mind was, how does this time series continue on the right? How do we extrapolate into the future? Do the numbers rise? Are they falling already? How much are they going to rise? Are they going to come down? That was the problem everyone was facing. So there are maybe two cartoonish ways of solving this problem, depending on whether you're in the simulation community and you're a straw man from the simulation community, not an actual simulation expert, or whether you're a straw man machine learning undergraduate student, maybe. Maybe let's start with the machine learning person. So you could think of this as a regression problem, right? There is a curve underneath, some smooth function that goes up and down. Knee-jerk reaction is, I'm going to use my favorite machine learning model, like a deep neural network or a Gaussian process regressor or whatever you like, to extrapolate on the right. If I use a ReLU neural network with 2 hidden layers, then the prediction looks like this. You can see a black line connecting the dots, right? So I'm guessing you all agree with me that this is a pretty useless prediction. Depending on how you choose your model, it can also extrapolate linearly upwards or exponentially upwards, or I don't know, something silly that you may want to make it do. None of these predictions are going to be useful because they don't capture the mechanistic structure underneath this data. They just use some smoothness assumptions about the function, and then extrapolating is not going to be particularly useful. So to make this algorithm, to make this data set useful, you have to inject some scientific knowledge, some mechanistic knowledge into your algorithm or your model. And such a mechanistic model could be maybe not a law of nature, but a model for infection processes like the SIR model. So I'm guessing most of you have seen SIR type models before. This is a very simple reduction of this problem here to 3 dimensions. We separate the population into 3 groups. You're either susceptible, so you haven't had it yet, you're infected, you currently have it, or you're recovered, you've already had it. And this is clearly an ordinary differential equation. So here are 3 states. This is a time derivative of these 3 states. And what this differential equation says, so P is the size of the population, it's just a constant. It's like 82 million for Germany. And what this says is, when infectious people meet susceptible people, then the susceptible people become infected with a certain rate. That depends on how often people meet. And they move from this group into this group. So these 2 terms are the same up to a sign. And then once you are infected, a certain percentage of all the infected gets moved to recovered or diseased, depending on how you want to make this model. So this is a mechanism. And this is an ordinary differential equation. So we can feed it to this wonderful piece of Fortran code. It's exactly of this type. And in fact, I did that. So I fed it to the solver, and that's the curve that comes out. This is equally useless. It's just as useless as the black line you saw before. It's a different kind of curve, but it's also useless. And actually, when I made this curve, maybe you realized that I had to inject something that I don't know, which is this contact rate beta and the recovery rate gamma. because I didn't know what it was. So I just played around with it a bit. It's just two numbers, right? And this piece of code is very fast. I played around with these two numbers until the curve at least fitted over here. But other than that, yeah. So the problem, and many of you will know, with these kind of models is that they actually always produce, for the infection counts, these bumps. They go up, but then they come back down again, and then they're done. And there's no way with this equation to make a curve that has 3 humps. So before we go on, let me maybe point out what's happening here on the algorithmic side. So we have 2 pieces of algorithm, a neural network and a simulation method. And so the neural network, let's put that aside for a moment. Let's talk about the simulation method for a moment. That simulation method, on the one hand, requires us to provide something we don't know, which is this contact rate. But on the other hand, it also doesn't allow us to use something we do know, which is this data. So these red dots in the plot, they don't enter this algorithm at all. They are not part of where this red curve comes from. It's completely detached, right? So now, of course, what's the problem? Well, so what's the problem with this curve? Can anyone guess? Just to make sure you're not falling asleep yet. David.
Maybe that beta is not time invariant?
Exactly. Exactly. So we all remember that around here, we were all told to flatten the curve, to go back home, to stay home, to lock the doors, and wear masks, and so on and so on. And what that did is it changed the contact rate. People didn't meet each other that much anymore, and then that meant the curve got flatter and moved down. And then, you know, we got all a little bit carried away in the summer of 2020 again. And well, then we went through this cycle of more and less contact. So a way to simulate this is to turn this function beta, sorry, this number beta, this scalar, into a function that varies through time. But that, of course, makes the problem in many ways much harder. Now it's a function we need to learn. So, of course, there are ways of solving a problem like this. And it's not like I'm the very first person to think about this, because you all know that there were actually research groups in Germany working on this data. And the solutions that exist for this kind of problem come under various names. They're sometimes called simulation-based inference, or approximate Bayesian computation, or neural ODEs, or depending on who you ask, they have many different names. They always boil down to the following idea. First of all, yes, we've realized that we need to have a function in here for this contact rate. Then we're going to approximate this function somehow. So we use one of these flexible machine learning models, like a neural network or some parametric model that you like, that you might not want to call a neural network. And then we make an initial guess for what this is. And we use this initial guess for this curve, feed it into our ODE solver, this piece of Fortran code I've now shown you twice. It produces a curve. And then we compute a residual between the curve that the simulation method produces and the data. And ideally, we compute a gradient of this residual as in terms of the parameters of this function, and then iterate, run an optimization method. Maybe not an optimization method. If you want to be Bayesian, we could use a Monte Carlo algorithm, so sample, or all sorts of other loops that we can wrap around this closed box called the ODE solver. So what all of these methods do, what they all have in common, is that there is this thing in the middle that is called the ODE solver, and they don't touch what it does. It's just feed in, come out. There's actually, maybe as a side note, as a historical note, a problem with this kind of approach, which is that this beautiful Python Fortran code that I showed you, it doesn't have derivatives. It's not automatically differentiable. And depending on which community you're from, maybe you find it totally natural that a simulation method is not differentiable, or you find it absolutely horrendous that it's not differentiable. I've now worked with people from different communities, and I keep being surprised by which communities have already found out about automatic differentiation and which haven't. So let me tell you that computer code can, if it's sufficiently smooth, be automatically differentiated. So someone would have to compute a derivative of this piece of code. Thankfully, you don't have to do this because someone at Google has already done it for you. So here is JAX, one of the most advanced contemporary deep learning libraries. And here's a piece of code called JAX experimental.ode, which solves initial value problems. It's written by these guys, Matt Johnson and Jake Vanderplas, who were the original authors of this piece of code. Well, actually, are they the original authors? So they implemented something called dormant prints ODE integration. And there's a bunch of magical numbers stored in it. The first one is 1/5, and the second one is, the first one is 1/5, which is 0.2, and the second one might be 1/3, depending on where we look. So these are these magic numbers again. So this code now has a derivative of the output with respect to inputs, but it's still the exact same method. It's literally copy-pasted from the Fortran code into Python. It's now Python, so there's a dark background, but other than that, it's the same piece of code. And it also still has, let me see if I can quickly find the interface for ODE int. Of course, it's Python, so it's much, much more code. Here, it still has this exact same interface. You give it a handle to the function, tolerances, an initial value, steps, integration ranges. Actually, that's not the perfect. The actual one is the one without the underscore. Can I quickly find it? Not sure. Wrapper, ODE int. Yeah, so it has the same interface as before. So what actually happens inside of this code? Can we maybe think about what it does? Because then we might have to can think about whether this is the optimal thing to do. So if you look inside of here, what this method actually does is then it has probably a body function which repeatedly calls this ODE int, and what it essentially does, the magic line that really is important is this one here, which is, so for those of you who don't know JAX, this is JAX notation for a for loop. There's a map being applied to some loop. And what this is actually typical for, so the reason I'm showing you this example is, right, to explain that these algorithms have really been transported directly into the machine learning community. There has been basically no adaptation of these pieces of code whatsoever, and they now drive neural ordinary differential equations. So you have heard about, stable diffusion, the algorithm that makes these little invented images. It actually uses this code inside, somewhere deep hidden away. Something like this, not exactly the JAX code, but probably some Torch code. So why is this a problem? Well, because there's this for loop inside of the ODE solver, and that for loop repeatedly evaluates this function that we're trying to optimize. So every computer scientist knows that nested for loops are maybe not always the best thing to do. So how do ODE solvers actually work? So here is my machine learner's cartoon picture of how an ODE solver works for an initial value problem. Here is our initial value problem. So there is some implicit equation that says there's an unknown curve x, which is this black line here, which we don't know yet. We would like to know what this curve is. We only know that its time derivative is given by a function that depends on itself, and that's a nonlinear function. This is this vector field here in the background, these arrows, and we know that the curve starts at some initial value over here at x0. So there's this little black dot that you can maybe see, despite the VGA resolution, which says we know that the curve starts at this point. So now how these algorithms work is that because we know that the curve goes to this point, we can evaluate the vector field at that point. That gives us this little arrow. And this means we know that the curve goes in this direction, so we can extrapolate a tiny little step towards the right and make a prediction of what the true solution may be. That gives us a new point where we can evaluate the vector field again, collect more data, right, to update the estimate forward in time, take one more step forward, and do that again and again until we reach the end, the integration range. And then we say this thick red line, that's our estimate for the solution of this initial value problem under this ODE. So these algorithms step forward in time, repeatedly collecting information by evaluating the dynamic function and extrapolating into the future. So they're really iterating between estimation and observation. This is also called prediction correction for these algorithms. And as you can already see in this picture, you can implement this process using a Bayesian machine learning algorithm just as much as a non-Bayesian one. So here is a Gaussian process that estimates this curve forward. You see 3 samples from the posterior. And of course, it's a very broad posterior because it's just 3 steps. It's a cartoon picture. Let me just check my slides. So this is not actually exactly how this piece of Fortran code works that I've shown you before, but it's very close. It's very close in the sense that you can make these algorithms behave in a mathematical sense extremely similarly to these Runge-Kutta methods. In the sense that they have the same computational cost. So they cost an amount that is proportional to the number of steps that the algorithm takes. So it's linear in the number of time steps. Here, the number of time steps is 4 or 5, right? And secondly, you can make this algorithm converge in its estimation error very efficiently. So if you increase the number of steps that you allow the algorithm to take, then the error between the thick red line and the black line, the estimation error, drops like some high order polynomial. So for these Runge-Kutta methods, the one that I showed you, that order is 4 and 5, actually at the same time. It produces 2 estimates. That's why it's called Dorman-Prince 4-5. And there are actually versions of this algorithm that I'm showing you here for which this order is 11, if you really wanted to, just to show off. But it can also be 4 or 5. And so in this sense, these are sort of very similar, right? They are fast and they're converging fast. But this algorithm actually has a new property for which the old algorithms don't need a theorem, but this one does, which is that produces this region of uncertainty, so these thin lines above and below. And it's possible to show that the distance between this black line and the red line, so the error that the algorithm makes, can be upper bounded up to a constant in a worst case sense by these thin lines. So it actually captures the error in a meaningful way. So it quantifies its uncertainty, if you like. That's the mathematical part of how do these algorithms, what properties do they have? But what I haven't told you yet is how they actually work under the hood, how they're implemented. And this is maybe where another part of this community here in the room in a technical university can sit up. They are Kalman filters. So they are signal processing algorithms. These simulation methods, we call them ODE filters, they come, algorithmically speaking, as like a backbone, a spine, along which you can add in information. So we start out with a Markov chain of latent states. In this case, these latent states are all the states. So they are a complete description of the dynamical system. In this case, it's S and I and R, and all the time derivatives of S and I and R. So first and second and third and whatever number of time derivatives you want to simulate. And then we have a linear time invariant system. Actually, to be honest, it's a linear time varying system that can predict forward through time. So far, we can just predict because there's no knowledge yet. And now we can inform this Markov chain about pieces of information, and we can include those pieces of information in a filtering and smoothing process. In particular, we can inform it about the mechanism, the law of nature. In this case, it's our ODE, this SIR type model, by including what we call information operators. That's an idea of Philipp Hennig, who you've seen before on the picture. These are little implicit observations, or not actually, they're explicit, but they are like relational observations that say at particular points in time, the difference between the first derivative of the state and some function evaluated at the 0th derivative of the state is equal to 0. So the differential equation holds. So these two are equal to each other. Now, if this were a linear function, this f, everything would be easy. It's just a linear observation, a projected linear map in the LTI system, so just Kalman filtering. This, of course, this is an ODE, so this f is a nonlinear function, otherwise everything would be really easy. Since this is nonlinear, we need to linearize, and then we use the extended Kalman filter. And smoother, but smoothing doesn't really matter. That's a way to build an ODE solver, an initial value problem solver. And this algorithm then has the exact same footprint as this piece of Fortran code I've shown you before. You can give it a handle to f, it goes in here. It can choose its step size, and it calibrates and estimates its uncertainty. But of course, since this is a Kalman filter, there's absolutely no reason that we can't also inform this system about anything else we know about the system. For example, if I observe the curve at various points, if I actually observe the state, I can just condition on knowing what the state is as well. Just plug in a normal other observation operator that just says, well, I also have some numbers, those red dots on the plot, that say this curve goes through this point. And we can use, so if you had a perfect information about the system, if you know what the mechanism was, if you know the initial value, you don't need this data because it fully informs you what the solution is. But of course, typically, there's something in the differential equation that you don't know. There's some latent force. In our case, it's this beta parameter. So we can use this extra data to inform this algorithm about this unknown stuff. We just add to our state space a description of the latent force, beta at time t, and just condition on those two pieces of information. So beta goes into F as well, so those arrows point towards the information operators, but we don't observe beta, so there's no arrow towards Y, right? We can't see the latent force. We can't see how often people meet. So it's just a Kalman filter, and if you are an engineer or signal processing person, you've learned about Kalman filters in undergraduate lectures, you can implement this piece of code, and there's your ODE solver. You don't need the magic piece of rational equations anymore to do simulation. And your Kalman filter is going to have a gain inside. That gain is algorithmically similar to those magic pieces of numbers. It's just that the gain can adapt itself depending on how much information you get from different information operators. If you apply this kind of viewpoint to this problem I've just shown you before, oh, bad graphics, then you get a plot like this, which shows on the top the estimate of the algorithm for the trajectory of the system, just for the I part of SIR in red. And at the bottom, it's estimate, probabilistic estimate, obviously, for the latent force beta. So a few things to note about this picture is, first of all, this picture was created by running a Kalman filter once forward through time, and then a Kalman smoother backward through time without ever touching the data again. So for those of you who know about Kalman filters and smoothers, smoothing is just bookkeeping. It doesn't actually cost anything properly implemented. And so this is not done by iteration. There's no outer loop. There's no computer gradient, follow the gradient, call SGD or Adam or whatever you like. It's just through and done. The second thing you notice is that the curve goes through the data points. That kind of makes sense, right, immediately. It also predicts into the future. So there's already a simulation part in here, basically. And you also get an estimate for the latent force for beta. And that estimate is not just a point estimate, it's a probabilistic estimate. It's a transformed Gaussian process, approximate Gaussian process. So it's constrained to this domain that beta lies on, which goes from 0 to 1. And what you can see, well, I'm not sure you can actually see it, but maybe you can kind of vaguely make it out, is that this thing has a very structured uncertainty. So remember how the ODE works. Let me go back a little bit, show you this SIR CAD model again. Beta enters only in these two terms. So if you want to learn about beta, we need to see a non-zero value in this part of the equation. So early on in this process, the data is essentially zero, right? Until February 2020, there was no cases in the population. So if you have no cases, you can't learn about the contact rate because there's always a zero, right? Anything times zero is always zero. So it doesn't matter what we see, like we don't know anything about this latent force at this point. Then the first infection wave came through. And we can see that it's not an exponential increase initially. It becomes flatter. And that means that the contact rate had to come down. So we now become certain, you can barely see that this region becomes certain around here that the contact rate is low. Then in the summer of 2020, there were very low case counts again. Maybe you remember that people could go on vacation. And that again means that there are few people in the population who can create new infections. So we only get very few observations about contact events. And that means we become uncertain again about what the contact rate is. Then we get new waves to become more confident again about what the contact rate is. And now, of course, you could include some mechanistic or vague expert knowledge about what's going to happen here to adapt the simulation. Maybe you know that some policymakers have decided to, I don't know, close the schools or something else, and then you could use that in your simulation. So that's one example of a probabilistic numerical algorithm dealing with different sources of information at the same time. And like you polling information sources from the mechanism, from the data, from the disk continuously to build one estimate. and doing that in a way that allows us to schedule the computation efficiently. We only touch the data at points where we actually need it, and we use it to directly update estimates about parts of the latent forest that we care about. So this algorithm is now available. You can use, I'm going to show you some software libraries in a moment. And I should say that when I started this kind of work about 10 years or so ago, so Ingo said when I came to Tübingen for the first time, I started work on these algorithms. Back then, they were just a vague idea. And they didn't look anything as beautiful as this. And they were implemented super, super inefficiently, and therefore were extremely slow. So those times are over. We're now at a point where the algorithm libraries for this kind of functionality has become actually very fast. Not thanks to my work, but thanks to the work of the wonderful PhD students I get to work with. What you see here is for one of these initial value problem solvers, a so-called work precision diagram. So here is the error that the algorithm makes. Right is bad, left is good. And here is the runtime cost in walk log time. So you want to be in this corner, ideally. Low error, low cost. And what you see here at the top is our current sort of reference implementation of these ODE filters. That's the starred line. Then here is a standard ODE solver in Python from SciPy. So that's actually also a Wunge-Kutta 4.5 dominant prince pair. It's this Fortran code again. Actually, I can show you this because it's literally this code. So this code that I showed you before, maybe you've seen the URL up here. I can also go back. It's actually from SciPy. So that's exactly, this SciPy just contains Fortran code. So this is this code. And then you see down here, those two thin blue and green lines, those are Google's JAX code. So they're much, much faster because they're nice and parallelized and everything. And in this blue dotted line above, that's Nico Kramer's current installment of the code. That's his transforming this code into proper JAX, essentially. So what you can see is this algorithm is now basically as fast as anything you can hope for. It's faster than the SciPy code, it's faster than the Fortran code, and it's so close to this optimized code that there isn't really a reason to make it faster anymore. I'm deliberately showing you this because I hope that you might want to try out this piece of code. If you want to, then we have several different options. One is to use our didactic piece of a code library called ProbNum, which is simple basic Python. It's not very fast, but it's very flexible. You can roll your own algorithm. Or you can use a fast JAX implementation, the one I just showed you by Nico Kramer. Or if you're more of a Julia person, then you can use Nathanael Bosch's code. In my group, I have a Julia PhD student and a JAX PhD student, and they constantly bicker with each other over who can write the faster code. So they're currently quite close to each other. I've shown you one example of what you can do with this kind of code. I just want to highlight a few other things and then wrap up. And maybe just one thing, actually, and then maybe see if any one of you has more questions. Of course, you can include in this language of Kalman filtering and smoothing all sorts of other information operators. Not just direct observations or a known differential equation, but maybe some other piece of knowledge you might have. So for example, you might know something about symmetries in the system. So this is where the VGA resolution really bites me. So on the left-hand side, you can barely see something that looks like a ball of wool, a physical system orbiting in several dimensions. This is a Henon-Hyles typical benchmark problem for simulating complicated many-body problems. And this on the left is sort of the true solution. It's computed by a very high-resolution solver. It's actually one of our ODE filters, but with a tiny step size, so at very high precision. And then, so you can't really see it. Normally, it's very obvious. This has a lot of structure. So this is a system that conserves energy. That's the kind of information we often know about physics as well. It's not just that there is some differential equation, but there is additionally a Hamiltonian that's also conserved. So if you run one of these ODE filters with a larger step size, so much, much cheaper, then it makes an error. It makes a prediction like this. And what you can't see in this plot, because the resolution is too low, is that it breaks this beautiful, clean structure of this curve, because it doesn't know that these orbits have to preserve energy. So it kind of gets lost. It gets out of sync with the orbit as it moves forward. But what you can do is you can inform the solver about the fact that there is some other function called h, the Hamiltonian, and that's also a function of the states, and the time derivative of that function is 0. It's just another type of algebraic differential equation. If you add that in as another piece of information, you get out this curve, which is much closer to the black curve, even though you can't really see it, because you can't see the high resolution version of this plot. So, of course, there are classic numerical algorithms that can provide this kind of functionality. They're called symplectic solvers or geometric integrators. And some of them actually come out of the math department in Tübingen from my esteemed colleague Lubich. But they are, again, specialist pieces of code that can provide exactly one functionality, which is to solve initial value problems with a Hamiltonian. The nice thing about this formulation is that you have this algorithmic backbone, the Markov chain, and then you just throw in whatever information you have. So if you know that the curve also has to go through some points, you can make that curve go through some points. If you know that it follows some PDE, you include some PDE. If you know that it has a Hamiltonian, you plug in the Hamiltonian. If some expert comes around and says this curve has to be between 0 and 2 and it can't ever go beyond 2, it's possible to include that information as well. Or if you know that for a while the second derivative is positive because it has to go uphill, then you can put that in as well. Or if you know that this is from a paper that Nathanael wrote in ER Stats this year, if you know that your ordinary differential equation is actually a second order ordinary differential equation, you can tell the algorithm about this as well. So if you are an applied mathematician, you've learned that every higher order ODE can be written as a first order ODE, and that's true. But when you do that, you're actually throwing away a little bit of structural information about the equation, and it's possible to include that in these kind of solvers as well. If you want to know exactly how, then please read this ER Stats paper. Okay, I'm going to stop here and wrap up, because I also see all the food over there, and people are beginning to turn their heads. So the main messages I wanted to get across is, first of all, that computation, if it's non-trivial computation, is a form of inference, of collecting information. If you're computing something you can perfectly compute, then that's not a particularly informative observation. But maybe if you're trying to solve a very hard mathematical problem, and in contemporary AI, we always have hard numerical problems, then it's useful to think about whether your computation actually collects all the information that it needs, and whether it collects only the information that it needs, and in which order it collects this information. To do that, it's necessary to think about the information content of a computation. And one way to do that is to phrase computation as an inference process, as Bayesian inference, as multiplying a prior with a likelihood, because then you can consider the change in the shape of the posterior, so how much it contracts, how much entropy it loses, as a quantity that describes how much information is collected. This idea is called probabilistic numerical computation, and you can read more about it if you like in the textbook that Ingo already mentioned, that I now have already plugged for the second time. You can read it for free online under this URL. Of course, you can also buy it if you really want to. And you can play around with this code that I showed you for simulation problems, in particular using either this didactic piece of Python code or some faster versions of it. And we're also currently actually running a lecture course in Tübingen on these exact algorithms, run by the wonderful PhD students who have written some of this code. It'll be on YouTube in towards the end of the term. So if you really want to know much more about these algorithms, you can find out more then. Not just about simulation methods, but also about linear algebra methods, about optimization methods, and about integration methods. Thank you very much.
Thank you very much for this wonderful, inspiring talk. So, questions? Paul.
Thank you very much. This sounds really interesting. So I was wondering, what is the price we are paying if we replace, let's say, the hard-coded Fortran code or the algorithms that are below that with the new algorithms and
okay. So the marketing answer is you're not paying any price because these algorithms, so that's why I showed you this plot, right? So the lines are very close to each other. There isn't really a price to be paid. Now, of course, so here's a slightly more honest answer. Maybe two slightly more honest answers. One honest answer is if you open up a textbook about ODE solvers, in particular Runge-Kutta 4-5 Dorman Prince, you can read wonderful theorems about them and how stable they are and how they have all these wonderful properties. And our theoretical foundation that we're building on is, let's say, less solid. So we have theorems and proper results that show that these algorithms converge, that they have calibrated global and local error estimates. But for example, we actually don't have at the moment strict guarantees that they actually obtain these high convergence rates. We can just make algorithms that empirically run to 11th order, and then they work basically empirically well. That's one problem. The other one is, maybe more philosophically speaking, if you allow yourself to try out new kind of functionality and change the order in which the algorithm processes pieces of information, you can also go wrong. So here is maybe an, let me give you, like, actually give away the secret, the catch. So this set, I told you that this algorithm that makes this estimate in a single pass through the data. And that's actually true. So that's why we chose this example, because it's a nice marketing example, right? Single pass, not a complicated for loop. And algorithms that do this in a for loop are much, much slower. It works very well on this data set because this latent force is smooth on a length scale that is comparable to that curve up here. So that's why the scheduling in this algorithm is basically perfect, right? You get the information about this curve from this data at exactly the right time. Now, if you have a curve here that changes on a much different time scale, then this algorithm can actually be way less efficient. And then it needs several iterations. So you can build a for loop around those algorithms. Then it's called an iterated extended Kalman smoother. Yikes. And then you can still run an auto-optimizer, but it can, for more rigid structure, can actually work much worse. And you can think of the most extreme case, if you have a constant latent force, where basically all of these black dots inform about the unknown quantity at once, it's actually better to run an outer loop. If you do that, then you can still do that in a probabilistic fashion. So if you want to read about such algorithms, I recommend a piece of code called Fenrir, again by Philipp Hennig, which addresses exactly this situation where you have just one parameter, or sorry, not one, but scalar sets of external parameters that you want to optimize. And then the probabilistic perspective adds a different kind of advantage. It actually allows you to regularize nicely. You can kind of take a detour to make the optimization easier. So it's not about the probabilistic bit, but if you're using an algorithm that allows you to change the order of the computation, then it's now your responsibility to make sure that the order is correct.
What is,
No, I think you were first, actually.
what if the dimensionality of the data is much larger? Do you pay a higher price because you have to track covariance matrices?
Yes. So the question is, what happens if the dimensionality of the problem is much higher? I also have a backup slide for this. So here's a PDE. PDE through time is a very simple PDE. It's a Lotka-Volterra multidimensional thing. So it's like a predators and prey in a Petri dish, like amoeba and bacteria eating each other. And so what happens here through time, so every frame is one time step, and every pixel in this image is one state in the latent, in this Markov chain. So there's a lot of these states now, right? Now, you know that, at least naively, a Kalman filter includes this local time step, which requires you to solve a linear system of size, number of pixels in this image, at least. And actually, time is a constant, which is the order of the solver. And that's, naively speaking, cubically expensive in that space. So that can be very slow. So how do you solve that? Well, you inject some additional independence assumptions. You just don't track covariances between all of the states, because you can imagine that the covariance between this pixel and that pixel isn't so high anyway. So you can get away with maybe a block diagonal Kronecker type approximation. And that's actually what this paper is about. It's from ICML this year, called Solving ODEs in a Million Dimensions Probabilistically. So yes, if you're building a Kalman filter, then you have to make somehow the state space sparse again, or the covariance sparse again. And we solve this in ways that also, admittedly, we didn't invent. It's kind of the knee-jerk way that everyone would solve these problems in a signal processing way, right? You just factorize, or conditionally factorize.
Okay, so the way that you explained, you have a solver, and
You have a system of ODE that you slowly have some parameters that you don't know, so you just bring in machine learning to kind of estimate those parameters for you. So what about other way around? So is it possible to just solve it as a regression problem and then add these kind of equations as the constraint?
Yes. So this is what you're, so for those who maybe in the back you didn't get the question, so what about turning this on its head and saying, let's do machine learning, but informed by laws of nature? This is actually called physics-informed machine learning, and there's a whole community around it now. There are big NeurIPS workshops on it in a month from now. And there's various versions of these algorithms that all boil down to saying we would like to have machine learning algorithms that know about the laws of nature and therefore are more sample efficient. They don't need to see as much because they know that there's an underlying law. Like the simple picture is, if I know that the curve has to look like one of these orange ones, then actually maybe I only need two points here rather than so many, and I already know what's going to happen next. So my take on this part of the community is that at the moment, a large part of the algorithms being used in that community are of this classic nature, that they are wrappers around the internal simulation methods. So they are wrappers around ODE solvers, around PDE solvers, around typically actually scientific simulation code, which isn't necessarily PDE or ODE, could be a cellular automaton or something crazy, right? Without derivatives quite often, because it's, again, Fortran code from the 90s, but it's not the Fortran code everyone uses, so Google has translated it. It's the Fortran code one PhD student wrote 18 years ago, and it has worked since then, and no one is allowed to touch it anymore. And that means, so on the one hand, that means it's very difficult to change things, but it also means that these algorithms are often kind of inefficient. They're built by companies like NVIDIA and Google who don't have to care about compute, right? And they're just wrappers that either optimize or sample or emulate. In every case, they just use these PDE, typically solvers, as a data source, but from the outer perspective. And that ignores the fact that inside of this box, there is another machine learning algorithm. So for example, there is algorithms from NVIDIA that learn to solve PDEs by calling PDE solvers many times, and then interpolating between them. So if you know that inside there's already a Gaussian process regressor running, right, essentially, then why not make use of that?
Another distribution, and we're able to kind of sample from that through the ODE, but we would like to have like a Jacobian as well, so we get the density of the resulting distribution. Would the methods you're developing or some of the things you talked about enable us, from your understanding of what I'm trying to describe, enable us to get a Jacobian ODE?
Yes. So in particular, both of these, like the Julia and the JAX code that I mentioned here, are differentiable, so they provide Jacobians. That's the simple marketing answer. Again, maybe a bit more careful if you're solving an SDE. Sounds like you might. Not sure if it's a normalizing flow or something. Then they don't necessarily do that. But we are in Tübingen, so maybe just send us an email and we can talk about. That's actually an interesting question, how to do that. And also, the honest answer is, if you just want to have an ODE solved with a Jacobian, then you can also use Google's code if you really want to. But then again, there isn't really a need anymore because you're just choosing between the blue line and the light blue line. So whether it's this or this, maybe it doesn't matter so much. No one else? Then David.
Questions?
Yeah,
David.
so in graphical models, you can perform efficient inference if they are trees, and for this Kalman filter, it's a tree. And I assume if you solve a PDE, you also solve it like as a tree because it's linear in time. What if you have a stationary PDE?
So the question is whether these graphs are trees. They're actually even more than trees. They are chains. So it's a tree that doesn't branch, right? Like a single stalk, basically.
But if you have observations,
Okay. But the observations are always filled in, right? So that doesn't really cause problems with this. Is not a. It's still just a chain. You can take this part and fold it up here, and then it remains a chain. so we use additional imposed assumed independent structure in the state space. Right? So if this is like million dimensional, then we say we're only going to track the diagonal of the covariance or a Kronecker factorization of the covariance and so on. But there is this, the algorithm is actually really just forward, backward.
Yeah, but if you solve like an elliptic, I think PDE,
So
then you don't have the time structure.
yes. So if you're asking about a stationary solution to a PDE, then you would typically just ignore everything to the right. You just have, there's just one thing here, right? And then everything happens in that one space. And that might mean that you have to really carefully think about how to do independence assumptions. And well, all I can say is Ingo and I are currently in a conversation about how to do this correctly. And you might, at some point, I would have told you a month ago that it's going to be on archive any moment now, but then it's not yet. So you know how these papers go, so who knows. But sooner or later, you can hear about PDEs as well, stationary in time. Okay.
Further questions? It would be your turn again. No worries, no pressure. Okay, any other further question? If this is not the case, let's thank Philipp again for this wonderful talk.